Welcome to this video. In this video we will talk about noise in circuits, and we'll introduce several concepts that are important when you are looking at noise in circuits. So to begin, let's start off by drawing a circuit. This is my circuit, and it's full of resistors. There may be voltage sources, all sorts of good things in the circuit. We typically think about two types of noise. One type of noise is what we call intrinsic, which I can't spell today. Intrinsic. Okay, intrinsic noise is noise that is caused by elements of the circuit. So for example, these resistors, it turns out, will probably be creating noise. And if you have a transistor, that transistor also will be a source of noise. Diodes are a source of noise. So intrinsic noise is noise caused by things that are inside the circuit. Extrinsic noise is noise caused by things outside the circuit. So for example, if you've got power lines, this is going to be an artistic rendition of power lines. So you can see the lines going off into the distance. Extrinsic noise, well, power lines, for example, radiate electromagnetic energy at 60 Hertz, at least in the United States, where that's the frequency used by the power distribution grid. So sometimes the extrinsic noise will come and attack your circuit, in the sense that if you have a long wire in your circuit, this will act as an antenna, and there's a chance that it will actually pick up these 60 Hertz signals. So in general, intrinsic noise is noise that comes from outside the circuit. To talk about noise, we typically will define it in terms of a voltage, Vn, sometimes a current, but those are typically the two ways we talk about it. And you'll recall that power, at least if I have power that's dissipated in a resistor, it would be equal to Vn squared over R. Or if I have a current, it would be In squared times R. Usually we have to characterize noise in terms of power, and we'll explain in just a minute why that is. Because noise is a random phenomenon, it's quite often difficult to describe it in any other way. But before we do, having just gone to all this effort to define power as a voltage and a resistor, we are going to get rid of the resistor. The idea being that power is proportional. So now I can say that the real power, the actual power that I measure, is proportional to the square of the voltage, or it's proportional to the square of the current. And this resistor gives me the constant of proportionality. In talking about power and noise, particularly in talking about noise in circuits, we will define our power to be, say, voltage squared, or sometimes current squared, but usually it's voltage squared. And then we will express our power in terms of the units volts squared. Now again, we need to understand that this is not power in the sense of physically dissipated power, but this is a quantity that is proportional to physically dissipated power, and the physically dissipated power just depends on the resistance. So that's how we'll end up doing this. If we look at noise, so So for example, if I were to plot a noise voltage as a function of time, sometimes it might be a deterministic signal, this nice sine wave, which is changing with time. This would be, for example, extrinsic noise that we get from 60 Hertz power lines. Or perhaps it might be a signal that looks like this. This is what intrinsic noise often looks like. But in either case, you'll notice that the voltage is actually changing as a function of time. And because this voltage is changing as a function of time, the instantaneous power is also changing as a function of time. And quite often it's changing randomly. It's doing things that we can't predict beforehand. That's not good. That makes it very difficult to work with noise. So what we will usually work with is an average power. And I'll show it as average now, but it turns out that from now on we'll just assume that we're talking about average power. And the average power is given by taking the squared value of the voltage and averaging it. So this line over the top of it means averaging it. Now I have to be a little careful when I talk about how I am going to average this. If I have, for example, this cosine waveform that we had up here, this guy, then a time average would give me the average power. So I take this sine wave or cosine wave, I square it, and I average it over one cycle. That would give me the average power. So when you're dealing with extrinsic noise, quite often you will average over time. Okay, so we could have an average over time. However, if this noise is random, say the type generated by thermal noise or by thermal noise in resistors, then this average over here will be not an average over time, but what we call an ensemble average. And until you have probability theory, this probably won't make much more sense than that. The basic idea is we look at every possible value that this voltage can have, we square that possible value that the voltage can have, and then we multiply it by the probability that the voltage actually has that. And we do that for every possible voltage. That neglects a lot of the real life issues in doing that, but the idea is that we average over an ensemble, and so we get an expected value. Okay. In either case, we can talk about this term like this, either averaged over time or over the ensemble as appropriate, as a mean squared value. Again, mean is essentially another term for averaging. And we've taken the voltage and squared it, so it's a mean squared value. And what we will do is oftentimes we will use this, clear out a bit of space over here, as follows. We will define an RMS voltage where the R is root, the M is mean, and the S is squared. Okay, and you can see that if I have this guy here, which is my mean squared voltage, if I take the square root of that, then I could say that the average power, but I'm going to drop the average bit on the power now, is equal to the RMS voltage squared. Okay, this is a useful result because it basically it turns out that for many noise sources, it's actually not that hard to find an RMS value for the voltage. In fact, it's actually much easier to find the RMS value for the voltage than it would be to try to find the instantaneous voltage. And so we can use this relationship then to talk about power. Okay, so I think with this we'll conclude this video. We've already gone 10 minutes. We've introduced some basic concepts associated with noise. In the next video, we'll introduce the way that noise depends on frequency. So join us for that.